In this part of the video, we are going to discuss data cleaning and preprocessing from a practical perspective using R, okay? And we will take into account the different concepts that were mentioned in the first video. To start with, I'm going to take a look at a fictitious data set that you have here, a fictitious data set that you can just have a brief look at, and you will see that this data set is, we are taking it's like a day by day snapshot of a campus life, all right? This data set is a day by day snapshot of a campus life. For example, you have a campus of University at Eben, Mocha, etc., and Redui, let's suppose. We are taking this like it is here. You have several variables and you have a record ID for each of these. You have information pertaining to temperature, climatic situation. You have information pertaining to the campus itself, and so on. Okay. For more information on the data set, without taking too long on that, I will show you the data dictionary here that is going to be uploaded on Google Classroom. You will see here that there is a record ID, which is a unique row identifier. You have a date, which is in that particular format. You have other information like campus. You will see that there is Redui, Eben, the site of observation, and then you will need to check here whether everything is written correctly, for example, things like that. You will see, for example, here, let's just check this. You will see that Eben is E capital, B capital, and so on, and this is not the same as the others. You will see that there are quite a number of issues everywhere. Even in the degree level, you will see that sometimes BSc is written like that, and other times BSc is written like this. And apart from that, you will find other issues where there are missing values as well. So there are quite a number of issues that you have in this data set that need to be dealt. Okay. And we are going to deal with these. I'm not going to show you all the issues at once right now, but we will deal with them. So I mentioned here some notes so that you understand. You will see that there is a problem in terms of a record ID where there are some duplicates. We'll get into that later. So you will see the different notes that I want to give you pertaining to this um, data set. Okay, so we have here, what are we going to do? I'll profile the data, I'll fix missingness and outliers if any. I will apply transform scale where necessary, and finish with um, a model on exam scores. All right, a model on exam scores using only genuine outcomes. So we are going to deal with all these, and you will see that even in the exam score there are missing records as well. So how are we going to deal with all these? We'll get into that in later. Okay. And you will see here, for example, there is card, capital CARD, small letter CARD. All these are different issues that we need to deal with. So here we are going to start by loading our libraries. As I repeat, I'm not going through the data dictionary for you to understand better the data. I would kindly request you to go through this data dictionary to better understand the data and what it is. So here, this is the data dictionary. You are required to go through it. Okay. So let me just close that and get into the analysis here, into the pre-processing rather. We start by loading our different libraries. That's the first thing. I will load different library. For example, I will load library dplyr. What is the purpose of this library dplyr? It is used for profiling, for the profile of the data, for basic wrangling, and um, normally when I'm going to use that particular library here, that particular package, I will be using different functions. In this, you will see later on, there are different functions that I'm going to use. There is going to be the glimpse function, there is going to be the select function, there is going to be the where function. There are many functions like summarize, across, mutate. All these different functions are going to be used from the dplyr package. And as I mentioned to you, it's used for profiling and wrangling. Then there is another package that I want to download here, to load rather, which is the string R package. Now, this string R package is used for text cleanup. All right, it is used for text cleanup. In this package, you will see that I will use functions like str to lower, str detect. All these are different str. Let me just write it down quickly just to give you an idea of what I'm referring to. Str detect, str to lower, str squish. All these are different functions that are going to be used from string R. And then there is another package that I'm going to load, which is the tidyr package. Now, this tidyr package is used for missing data helpers. All right, there are things like fill that I'm going to use a function fill. There is a function drop na that I'm going to use for this from this package. And finally, I will be using another package that we will call nanyar. Nanyar is what the package nanyar is going to be used to apply the little mcar test. It's going to be used to apply the little mcar test. So I will run a function you will see later called mcar test, and that function will enable me to know if the data is missing completely at random or not. In a nutshell, these are the packages that we intend to use. And to start with, obviously, the first thing that we would want to do is to load the data. I'm just going to copy and paste the path of my data. Here we go. Uh, I'm just calling my data as df, and as you would have noted here, all the backward has been changed to forward. And then you will see that there is an additional thing that I have included here that maybe you are not used to. This is an a.string is equal to blank. What does this mean? Anything that you believe your data uh, contains that should be considered as a missing value, you can include it in that argument here. For example, me in my data, the missing values that you have are generally blanks. You will see here. Let me just move on this left here. You will see, for example, here, if you go through the data, let's take a look at degree level, for example. You see that there is a blank here, and you see that there is a blank everywhere. These different blanks are meant to be our missing values. Normally, this is what we will consider as missing values. But let's suppose in your data, if you had a value of 999 for ozone, if you see that ozone is all these different values, and then let's suppose you had a value 99999 which you wanted to consider as a missing, you could include it in there. Let's suppose if you wanted to include as a missing, you could include it here by saying any value that is 99999 in my data should be considered as a missing. But be careful, that takes the old data set into account when you are dealing with this, when you're changing 9999 to na. But if in case one column of your data contain values in 4 digits like this, then or even 5 digits, then you have to be careful if this value makes sense in another column. But if this value normally can be used to represent a missing value, you just use it here. But for my case, there is only blank that is representing missing value, so that's why I'm running df with that additional argument here. I'm running the read.csv with an additional argument, including a missing. So what does this do? It will replace all blanks by NAs, including, meaning that it will include NAs in my data set when originally they were not there. So you can just have a quick view of the DF of data frame. There we go. And we can just remember there was a missing value in, here we go. There is a missing value in degree level. It is not blank. It is not appearing as blank, but it is appearing as an A. That will make things far easier for us to deal with later on. Now, that's how we are going to read our data. The next step now is obviously to have a look at the profile of the data. So what do we do about that? We'll start by a simple function that is called glimpse. And that function glimpse, obviously, it appears, it exists only under the dplyr package. All right, it exists under the dplyr package. Let me just remind you, this function glimpse exists only in the dplyr package. So we run it. So I think I forgot to load all these libraries. I've noted them, but I forgot to load them. So let me load these libraries and then we continue. Now, there is one thing that you need to remember is that if in case some of these packages you don't have them, if for example you don't have Nanior and so on, you will need to, before running library, before you get into library, just a kind reminder, you need to do install the packages, and then you put in between inverted comma Nanior, and then you run this. It will lead you toward the cloud. Not it will give you. So let me it's already in use, but if normally you get you will get a pop-up, and this pop-up, when you do it here, because it's already in use, that's why I can't use installed packages. Okay, but whenever if you don't have this manual, you need to go through that step first, and then when you have gone through that step, it will lead you to a pop-up. You can just choose the cloud uh, when you're downloading, and then you leave it to download, and then when it is downloaded, it will give you some warning message. You don't need to worry about it. You then just run your library manual. That should work. Now let me get back to what I was doing. So what is this glimpse doing? This glimpse is just giving me a quick structure of the data, a quick structure of the data with the shape of the data. The shape of the data means the number of rows and the number of columns in the data, for example. It gives us a shape. And then you will also see the data type for each of these. You see that date is considered as character. You see that campus is considered as character. Campus should not be character. Campus should have been factor. But these are issues that we are going to deal with later, okay, not now. So but you see that the glimpse function is a bit like the str, if you want, str function, similar bit, so you can just get an idea of what's going on. Then you can also do a summary of df, which gives you another idea of what's going on in the data. As you see here, for example, you see that there's a minimum value of negative 500 for canteen revenue. That sounds to be something a bit strange and wrong, obviously. You will see that these are considered as character, record ID. You will have the minimum, the range of student intake. You have all these different variables to have a number of missings as well, and so on and so on. Now, all these are from summary. You can get this information. Now, if you also want to have a table, let's suppose if you want to get the missing nest by, what are we doing, by the way, right now, La? We are just working on the profile of the data, where the profile looks at the shape. We are talking about the missing nest. We are talking about duplicates in a moment, and we can just check range, for example, as you see here, the minimum negative 500 to 80,000, 82 to 153, all these kinds of things that we want to do. Obviously, these range are for numeric data. Remember that. And we can also, yes, these are the kind of things that we want to do in profile. All right, that's what we are going to check. We are doing the profile of the data right now. To do that, we need to work on the missing nest now. The missing nest, let's call it missing table. I want to obtain a missing table. We can already see it right now. You see, there are missing here, for example, 9. There is missing for exam score, there's a missing here, etc., etc. But you can create a table to make it a little bit more uh, easy to identify the missing values by doing data frame. What is data frame? Data frame is going to create a column where you have a variable and values. In one column, another column you will have another variable and values, and so on and so on. So let's start by creating our data frame, where first of all I will have a column called var, which is going to be my variable names. So the names of df, the names of df, by the way, will be solar radiation, ozone, ppb, etc., etc. All these are going to be the name of df. So I create a column with the names. So in one column you will have all the names on different rows. The first row, in the first column var, will be record id. The second row will be date, and so on and so on. And then I will determine how many missing values I've got. So I put a comma here and I determine the number of missing values. Let me call it NNA, the number of missing values. To do that, I just need to do call sums of df, but is.na. Call sum of df means, what does it mean? Call sum of df is.na. Call sum of df is.na means I need to go and identify what are the missing values that I have, and these missing values are characterized by the letter n, by na. And now, when you do call sums, it counts the number of NAs that you have by columns, by each column. So it goes in the first column. Let me just check the. It goes in the first column and try to identify the NAs. So, for example, in the record ID, there is no NAs. It will go in date and identify NAs, and compass and identify NAs. In the summary DF, you won't find the NA. But for example, here in the degree level, you won't find the NA because it is the summary and it is considered as character. That's why it's not giving you the NA as a missing value, because it will take it as a character. But when you are going to go in the degree level, whenever there is an NA, when you say is NADF, it will give you this information. So you see the disadvantage, the limitation of a summary DF here. You don't get all the NAs available. You don't even know if degree level has got an NA. But using this principle, you will know whether um, degree level, for example, has an NA, because degree level is character. Now, you can also compute the percentage. Let's call it PCTNA. And then this is equal to, let's suppose, 100 times um, col of means is.na. Now, when I'm doing the calls of means is.na, it will just find the number of, let's suppose I have how many columns here? We've got 222 rows. If I have two missing values in a particular column, the average would be 2 out of 222. The average would be 2 out of 222. And then this average means the proportion of missing values that we have. This is why I do call means. Just like I can do call sums, I can do call means. So I get the average number of missing values for a particular column. And then I just need to multiply by 100. So if there are two missing values, let me just run that. It means that there is 0.009 in terms of proportion of missing values for that particular column. So if you want it in terms of percentage, you just need to multiply by 100. So you will see that there is less than 1% of missing values in that particular column that you want. So what's doing here is that you are computing the percentage of missing values. So let me just run this more table, and then you can just quickly identify what are the tables that are problematic or not. So here we go. You will see that there are rows there are columns. Columns here means this record ID dates. There are column in my data, like record ID, like dates and campus, which have no missing values. But you will see, for example, in degree level, you will see that there are nine missing values, which represent 4% of missing values. And then the column that is a little bit more problematic here is ozone, and there are 21 missing values, which represent about 9% of missing values. It's still not that much, so we can deal with that later on. Right now, we are not looking at the solution. Okay, we are not looking at any solution for the time being. We are just identifying issues. All right, that's all we are doing. So we have identified the missingness. We are just doing the profile of the data, as I mentioned to you. We can now, just like we did for missingness, we can identify duplicates. We identify the shape. The shape is, where is it? The shape is here, 222 and 16 columns. Now we look for the duplicate. Let me determine how many duplicate rows I've got. For example, I want first of all to know if they are duplicate rows. So I just do let me say dup row count. And then this dup row count, I will say n row of df minus n row of df, but this time distinct df. So it will give me the number of, when I'm running that, it will give me the number of exact duplicate rows in the old data frame. In the old data frame. Let me just run that. To know which one they are, let's go quickly there. I already know which one they are, by the way, but for you, you can just create a column here and a blank column, and then you do 102 minus 101 or things like that. Or you can also run, there are different ways you can sort them out, the record ID. When you have sorted them out, you will be able to do an additional column, and you do this minus this to see if you get one, it's fine. If you get zero, then it means that there is duplicate records. There are different ways of dealing with that. So what are the duplicate records? For example, you will see that there is this 1035, which is reduit 150 and so on. Let's go down there. It's 1035, reduit 150 and so on. So R has identified these two records as completely as duplicate, as complete duplicate. There is another example here. If you look at row 93 here, 1092, you have eben 197. 1092, eben 197, etc., etc. So these are the two duplicate records that we have. So you will see that it gives you only two duplicate records, obviously. Now let us check the duplicates that we have on the ID column. All right. So you will see the ID column here. There are some duplicates. For example, here 2029, 2029, and then you have 20. Where is it? 20 1035, and you have 1035 again. You have others, you will see like 1086. You will have another place where you have 1086. You need to go and find it. And then you have 1092 and 1175. These are the different duplicates that you have in the particular record ID. I'm not talking about the full data set as duplicate here. I'm not talking about all columns being duplicate, but I'm not talking about the full row being duplicate, but I'm talking about that particular record ID having duplicate items in them. Okay, so if you want to identify how many duplicates, if you want to know, let's suppose to have a quick check to know if there are duplicates or not, you can do something like that. Duplicate ID count. Okay, duplicate ID count, and then you do sum, and we are going to look at the the record ID. You will see that I'm using DF dollar because I did not attach the data yet. That's why I'm using data DF dollar. Sum of duplicated record ID. And then in the duplicated record ID, I will also say na.rm equal to true. So what does this mean? If ever there is any missing value in the duplicate in the record ID, it will remove it and then compute the number of duplicates that you have. So basically, this is determining the number of duplicate record ID values that you have. So let's run this and see what we obtain. Here we go. We are informed that we have five duplicate ID counts on record ID. By the way, this same principle that you see here, you could apply it on another column if you wish. Okay, uh, if there is a need to check if there is duplicate, you can apply it on another column. Now, with respect to what I've just mentioned here, you have a duplicate IDs. I just mentioned to you which one they are. You have 1029, you have 1035, you have 1086, you have 1092, and you have 1175. These are the duplicate IDs that you have. You can just check them. And next step, you would recall in the lecture, I mentioned something like you want to do some diagnostics on the missingness to observe if the data is MCAR or MAR. And the first one, comparing the means and the means, for example, among observed and missing, might be helpful to determine whether the data is MCAR. Through this, you may also know whether the data is MAR. That's generally what we mentioned in the first video. So I want to do something like that. What do I expect? What do I want to do? I want to have something like, for example, I'm going to focus on the ozone data. I'm going to focus on the ozone data, the ozone variable. And there are 21 missing here. And I want to work with that to see if the data is missing at random or missing completely at random, things like that. How do I go about that? So I will have, for example, a column called ozone missing. That's one. And then I will try to see the pattern of missingness by campus, and also um, when I'm going to get that, I will try to compute the mean by campus, the mean temperature, all right? The mean temperature. So we will look at two different things here. We'll be looking at the behavior of these missing values with respect to campus and the temperature as well. So we will check on that. We will compute the mean temperature to see if the temperature varies by campus when there is missing or when there is no missing. And the additional thing that I might want to do is also to count how many you have. But it's mainly the mean temperature that I would like to look at. So how do we go about that? First of all, let me delete this and let me do something. So for this particular exercise and also for other exercises that may come afterward, maybe it's good that given that I'm working with campus, working with campus, and given that you know that campus, let me just go back here. Given that you know that campus is character, we might have to change certain things here. How are we going to change certain things? We'll leave it as character, but you would recall rather. Let me just find this out. Where is this? Yes, you have, for example, a situation. Let me view the df, it's better. I'm not able to see it here. If you view df, you will see that there is eben, mocha, réduit, and then you will see that they are written quite differently. For example, here, look at that. You see there is réduit written differently. So we want to bring some, uh, how do we say? We want to bring some consistency in the way things are written here, right? So that we don't have, when we are doing this small table that I mentioned to you earlier, but I just mentioned to you in a few 1 minute ago, a few minutes ago, the table that I just mentioned to you. If you want to group by campus, we don't want to have one moment eben here and then one moment eben written like that. So we want to ensure that there is consistency. So I'll deal with these things first. So then we can move on to the next. We are going to take the data frame that we have and replace it using the pipe operator. What are we going to do? We are going to do some amendment where we are going to change campus, and also I will at the same time change date as well, even though I'm not using it right now, but I will do the change because date is in character as you saw earlier, and I will change that to date format. That's one thing. So let me just do two things at the same time here. We'll start by using the function mutate. So the function mutate means that you're creating a column. You are just doing creating a column. Like for example, here I'm creating the column campus, which is already campus, and it is going to override it. And that column campus will basically need to trim extra spaces. That column campus that we have. Let me just show you that. We'll just do some amendments to that. It will trim extra spaces if in case we have, because if we have EBEN, there is a space which you don't see here. And if there is EB and E without a space, maybe these will be considered as two different campuses when they are the same. So we want to trim extra spaces and also fix our things like, as I mentioned to you earlier, EBEN like that, réduit, for example, write it as small réduit normal like that. This is called title case, all right? We want to change to title case, that is the first letter appears as capital and the rest stays as it is. So I want to do these kinds of change on campus. So in other words, I will say campus equal to be able to do that, I do str to title. When I do str to title, there are two things that I'm doing. Str to title is basically going to fix my data, that is things like eben will change to eben. And then on the other end, I don't want only to do that, I want also to trim extra spaces. So for this purpose, I will say in the same function, str to title, I will write str squish, and then I will say campus. What is this? So here, what we are doing in this particular code is very simple. I am, number one, ensuring that there are no extra spaces available. Squish function is a very interesting function because you see, if you write something like eben, let's suppose I write something like that, eben campus, and then I have more spaces like that, okay, something like this. So using this squish function, it will not only solve the issue of trailing and leading spaces that you have. The leading and trailing spaces, these are trailing space, these are leading space here, that it won't only look at that, but it will also collapse these internal white space that you have here, right, to single space. So in other words, it will change that into something like this, a ben campus. That's what it will do. It will change that into something like this using this squish function. So what we are doing here, we are applying this squish function just to remove any sort of unnecessary space, whether internal or trailing or leading. Though we are not worried about the internal one because it's only a single word that we are using, but still it will remove leading and trailing spaces. That's the advantage of that function squish. Then when it has removed that trailing and leading space, as you are seeing, then we can apply the STL to title, where I'm making the data title case. That is, if, for example, if I've got something like this, as I mentioned, it will be like that. Okay, so that's kind of what I want to do for the time being. So I'm doing STR to title and from the squished one. So let me just check that. So this mutate is for the below. Yes, this is one thing that I want to do with campus, as I mentioned, and then I want also to change date. You would recall that the date is in terms of character, so I want to change that and make it as dot date. When I put that as dot date, then it will automatically change, convert the date column that we have from text to real date. That is essential because if we want to do some month grouping later, we can do that. Okay, but well, for the time being, we're not necessarily worried about the date yet, but still, I'm mentioning it in case we need it. All right, so we'll just run that. So there's a mistake somewhere. Let me just check that mistake. Error. I think I've put this zero here. Let me just remove that. Here we go. So we have our data frame now that is, let's just take a look at the data frame again, df. So you see that now it is date, as you are seeing. It is date, it is not anymore character as it was earlier. The second thing I want to check is to view the data frame again. And let's just check. So we have a problem here. I believe that the reason that it's not working properly is because it is not passing the character correctly to the date format. And I believe that to solve this issue, we might have to state the format here, and that should solve the issue. All right. So let me just include the format of date here. So I will say the format, and to know the format of the date, we just need to check our date column, which is here 1/10/24. So you see that it is in terms of month, day, and year. So what do? We write down. I already explained that in one of the video, if I'm not mistaken. So here we go. We are going to write down capital Y. You will see that I'm using capital Y. A Now, this capital Y, obviously, because our data is written in the form of 2024 and not 24. If the data was 24, you would have put small letter y, but here it is capital Y because we are dealing with the full date. So let's run this again and just check. Oh, it's still a problem because I believe I forgot. We need to remove the data frame first. RMDF. Let's remove the data frame and run the whole thing again. That should work. When I say RMDF, it means that I remove the data frame because we have done so many changes. You will see that if you view df, it won't work now because it's no more in the memory. So let me just delete that and run the whole thing from the start. Okay. We'll remove this view df again because I don't want it to do that. So let me just run the whole thing again. Let me clear that window here and run the whole thing. The whole thing should work now. So let's have a look at view df. Here we go. Now it has worked well. So we took some time with that, but it's okay. It happens. Now, the next thing is when I've done the necessary changes, we can just have a look quickly. By the way, I forgot to check that. Let's view df. And let's have a look at campus. You see that now there is no more this issue of campus eben or registry written wrongly. I'm scrolling around, I don't see anything. So it seems like everything is okay. Now, having done so, the next step would be, as I mentioned to you, I want to find the average of temperature by campus, not by campus, but by, yes, by campus, and also by missingness. How do I go about that? To work on that, what I will do is that I will take the data frame again after having done the changes. I will take the data frame. I'll pass it on to, excuse me, I'll pass it on to the function mutate. What do I want to do with that? In mutate, I will normally create, so I take the clean df, as you are seeing, take the clean df and create a new, what I want to do is to create a new true or false flag. All right, as I mentioned in the video earlier, in the first video, uh, video one. So I want to create a new true or false flag and see if ozone is missing or not missing. You will remember that there is the ozone. I want to know where there is a missing or not. Where is ozone? Here we go. Here we go. So we want to check. You see, for example, there you have ozone ppb, but I will create a new one that we call oz missing, and then this would appear as false everywhere. But here in that column, it will be considered as true. So that's what I'm going to do. So let me just do that. So I will say group, not group, but mutate, and then I will say oz missing is equal to is.na. I'll put that here, is.na. So we are doing something like this, where in my mutate function, I'm applying this. So let me just put that here. I'm not going to run it now because I've got something else that I want to do, but just for information, this is basically doing creating new rows in your, if you want, I can just run it and then I will remove the data frame and just show it again to you. So let's just run df. You will see that it creates a new column at the end, which is called oz meeting. You see oz missing, sorry, and then you will see that there are false, false, and then the moment that appears, a missing appears, it becomes true. So what am I doing that? I'm just mentioning earlier, just to check for if the data is missing at random or not. So I'm not over yet. I want to apply the pipe operator again. And now I'm going to do a group by, because you would recall earlier what I wanted. So I do a group by. I'm not going to repeat that. You can just rewind the video. You will remember that I wanted to have it by um, true or false, and also not only by true or false, but by campus as well. So I want to group by these two, and then I will apply the pipe operator again, and then I want to find the mean. To find the mean, I will need to do summarize as a function, and the summarize function that I'm going to apply, it will be based on a new variable that I'm going to call mean temperature, and that mean temperature will take the mean of my temperature data. Let's write it properly. So you will have a temperature, it's not there. Here we go. You will have temperature written as temp C. So we'll do temp C, and then if in case there are missing here, we are going to apply the mean without considering the missing values, obviously. If there are missing in the temperature, well, because we are looking at the missing in terms of OZ, but if in case there are any missing in the temperature, we'll just disregard it. So otherwise, the mean may not function. So we'll do, and a.rm is equal to true, which basically means that if there are missing in temperature, just disregard it, so that we can calculate the mean of temperature, irrespective if there are missing in temperature itself. We calculate the mean and we group it by these two, OZ missing and campus. This remove, and a.remove is equal to true, is not about the ozone variable, but it's about the temperature itself. If there are missing, just remove it so that the computation can be done. And then you would recall also I wanted to have a number of missing. So this is how we can obtain the number of missing. That will return how many rows are in the group. In addition to the number of missing that you have, there is also an additional information that is good to do is to include some, is to remove a grouping that you have done, is to remove the grouping that you have done. What do I mean by removing the grouping? It's just an additional argument that we call dot groups. Now, when I say dot groups, it's not groups. I say dot groups. Dot groups is an argument that allows you to ungroup your data after the summarization has been done. You may ask yourself, why do I need to do that? Now, it's quite simple. Dropping the grouping after the summarization is important for one reason, is that if you keep this group, later verbs that you use in dplyr, like summarize later, if you want to do a summarize later, if you want to do a mutate filter, etc., that can run within each group, and it's not a very good thing. If you ungroup the later verbs that you are using, summarize, mutate, filter, and so on, will normally run on the old data again. So it's like you are dropping the grouping after the summarization. You are grouping by those missing and campus. You don't want other codes that you write later to stick to that grouping, because um, normally when you are calling the when you are using group by, there is a small issue, is that it sticks to your data frame. It sticks to your data frame. So it's always a good idea to drop that particular grouping after you have done your summarization. That's how you do that. You will put an additional argument after the n in your summarize function that allows you to do so. Then, after having done the group by and removing the grouping afterward, I can also add something else, that I want to order the data. So let me just run that first and just check. Mm, yes, let me just quickly type df and see what we have here. Let me just run that again. And then I type df, and that's what I get. You can leave it as it is, but you could also, if you want, make the those which appear as missing appear first. All right. If you want, you can bring all those missing, all those that are missing appear first. By the way, LGL means logical, huh? Logical data type. So if you want this small update, you can just add an operator here, and then you do arrange, and then you want to arrange by who's missing. You want to arrange by who's missing, and then because right now it is F and T, you want it to be in descending order where T appears first and then F appears second. So you do descending, and then here we go, and then we can run the whole thing again and just check it again if it works well or not. Let's have a look. um, so excuse me, I just need to put this a little bit down here. Yeah. Let me just remove df again, and then I'll run the whole thing from scratch just to avoid any problem. And then I will do df again, and then you will see that now true appears first and false appears second. So here we observe in this situation here that there is a mean of temperature of 28.5 for Eben with regards to ozone values missing. That is for all those ozone value that are missing. Let me just go back to the data quickly and just give you an indication of what I'm talking about. So I'm referring to all those data filter, and then all those missing values from ozone here, all those missing values from ozone, and I've done an average of their temperature. It is 28.384 as you can see in Excel, and we are just getting that here for, sorry, not for everything, but for Eben. Let's just now filter by Eben. Move reduce here, and you will see that the average is 28.46, which is 28.5, and that's what you get, the 28.5. That's basically what we just did here, eh? We have done a filtering of, we have just basically been obtaining the average of temperature with respect to all those missing observations from ozone for Eben. Then we do the same thing for Redui, for example. The missing for Redui, we can compute the temperature for Redui, and then you will see that we get 28.27. So for Redui, 28.27, 28.3, that's what we get. So these are the kind of things. So then we can just compare for those where we don't have missing. Let's suppose I come back to Eben and false. Eben and false means what? I will go back to Eben here, and then I will run on all observations excluding the blanks. So then when I do the average, I get something like 27.3. So 27.3 is here, and you see that the average tends to be smaller when there are missing values. The average tend to be smaller. I repeat, the average for the temperature tends to be smaller when there are missing values, whereas this is not the case when you have observations. All right. Now, what does this imply? That could imply that your data is not missing at random, missing completely at random. That the data is missing at random rather than missing completely at random, because the pattern is tied to the observed variables. What are the observed variables? If we look at by campus, all right, if you look at the by campus here, the missingness tends to occur mainly for Eben and Redui. Mocha has zero missing. So if missingness was MCAR, what you would expect is that you would expect that there are some missing, that is some true values as well for mocha. But this is not the case here. So that's also an indication why we can say that the missingness depends on the variable of campus, because the probability of missingness for for based on campus of mocha is zero here. So that's we see that missingness tend to depend on the campus. So there's no missingness for mocha. On the other hand, when ozone is missing, the average temperature seems to be higher. You see that? The average temperature seems to be higher compared to when it is not missing. So that means the chance that ozone is missing depends on temperature. Context based on the fact that the probability of missing tends to vary based on campus. For example, Mocha is the probability of missing for Mocha is zero. So that's already indicating that it's not the same everywhere. It's not like the same for a band, it's not the same for a tree, it's zero for Mocha. So then the same thing, there is higher probability of higher temperature, sorry, there is missing for higher temperature, indicating again that data, the missingness depends on these variables somehow. And here, temperature tends to be an example of an observed variable, just like campus as well. So logically, it's clear that when you look at this um, mean, the average temperature and so on based on missingness, it's clear that the data is not MCR. It rather matches the definition of missing at random. In other words, missing conditionally at random, which is the same as missing at random. So here missingness can be explained by observed variables. I would encourage you to go through the overview video that I made where I explained to you the concept of MAR, MCAR. If in case you are not getting what I'm mentioning here, please go through this video that I've given you. Now we will go for the Little's MCAR test that I mentioned to you there. You will know that I've mentioned something like mentioned but not mandatory. Still, this is a very important test to do to be able to check whether your data is MCAR or not. When I refer to your data as MCAR or not, I'm not going to use the full data set, obviously, to do that. I will be using only data that will enable me to check if the data is MCR. How would I know that? Because the Little's test, Little's MCR test, is normally a test that is based on a chi-squared distribution. So the fact that it is based on a chi-squared distribution, it obviously implies that you are dealing with quantitative data. So what I will do, we are going to run that and we are going to see what result we get from that. So to run the MCR test, let's find the MCR variables that I want to choose first. For that, I will run the select from dplyr, the select function. I will choose only the variables that are of interest. To know what are the variables that are of interest, I can do glimpse. I can also do str and df. I will basically. So here I have a small problem here is that I have defined this as df when I should not have defined this as df because I'm not getting all the variables that I want here. So sorry for that. I should remove that df object again. And when I remove that df object again, I can now run the whole thing again, sorry, because I should not have assigned this as df. I should have just run it normally. So let me run the whole thing again from scratch. I'm sorry about that. Let's run that. and here we go. We get the table again. There you will see that there is no need for me to call df. Now, to know what are the variables to select in df, we just do that again, and you will see what are the different variables that you have here. Now, when you got all the variables that you are seeing right here, we can just choose the numerical variables. We'll start by electricity, kilowatt, for example. So we have electricity kilowatt, excuse me. We've got electricity kilowatt. Then we've got ozone, um, ozone layer as well. What is the ozone, ppb. We got solar variation as well. Radiation, we just copy that here. We got the wind MPS. And then you've got the rainfall, but I'm not going to select the rainfall. Uh, I would rather choose the Dempsey. Why I'm not choosing the rainfall? Because you see the rainfall contains uh, zero values, as you are seeing here, and it is an integer normally. And when you are running the Little's MCAR test, it usually assumes approximate multivariate normality. And I'm not getting the details of this model, but given that it assumes multivariate normality, approximate multivariate normality, the little MCR test may become a little bit less stable when we have such types of values, especially when you have um, so many zeros, for example, right? It's what we call zero inflated data, uh, or we can say zero skewed. This is the type of data that you have here, and it's preferably not advisable to consider such type of data. Though, if you could include it if you want, that would not be a big problem as such, but it is preferable just to exclude that and run the MCR test. Now, you will choose whatever variable you feel that it is necessary to use. You use them in the MCR test, there is no problem. So we are choosing our variables as you are seeing right now. And then what we can do is we are going to, let me delete this. We can run our MCAR test underscore test MCAR vals. This is the test that exists under the Nanyar package that I've mentioned in the beginning. So we can just run that test now. That even we let's run both of these. So first of all, you can just check MC. Let me just run that first. Oh, yes. You will see that electricity kilowatt is not found because I did not mention the data frame. So I need to set df first. And that's why you should not put df, because if you put df here is equal to df mutate, you are replacing the current df by a new thing, and then you would be using that summarization in your data. So that's why I kept the df as it is. So that's very important that we put the df, and here we go. We can run the mcer vars test. We will get all the variables related to what we have chosen, with the missing values whether you have them, and then you can run the test as you are seeing. Now, this test is very interesting because the Little's MCR test basically assume that your null hypothesis here, what is happening is that the null is that the data is MCAR. And of course, the alternative is the data is not MCAR. That's kind of thing that you have in this test. The test, I'm not getting into the details of the test here, it's not the purpose, but as you will see here, H note is such that data is MCAR, whereas the Alternative is that the data is not MCAR. So the little's test, if you want to report that, you will see that the test statistic, which is a chi-squared test, is 19. So then the p-value that you have, a degree of freedom is 21. The p-value that you have here is 0.588, which is far above 0.05. If a p-value is far above 0.05, this is a very important concept, by the way. If you have any test that you are doing, whether you are doing literal MCA or test or any type of hypothesis testing that you have, if you have such type of results where you get a p-value, irrespective of whether you are doing literal MCA or test or you are doing a test for the mean, a test for variance or whatever it is that you might be doing, a chi-square test, anything that you are doing, if the p-value is less than 0.05, that indicates that you need to recheck the null. So for whatever test that you are doing, you need to know what the null is and what the alternative is. Like in our context, we are running MCAR test. I just told you that the H node is such that data is MCAR and alternative is data is not MCAR. So in our context, we have our our p-value is equal to 0.588, which is far above 0.05. So if it is far above 0.05, it means that we do not reject the null. So if we do not reject the null, that obviously indicates that MCAR is not rejected. All right, MCAR is not rejected. So if MCAR is not rejected, that indicates that you can apply some imputation, but let us not forget something. Even if the result is showing you that MCAR is not rejected, we know that somehow we have MAR present based on what we have seen earlier. We have the missing at random um, present because we saw that there are temperature, there is campus that influence the number of missing values. So even though you see that the MCR is not rejected, you still need to be careful with regards to the MAR that you have. So whenever you have to impute values, ensure that you take into account campus as well. Okay. Um, so here, when you have such type of result, when p-value is greater than 0.05, which means that we do not reject the null hypothesis, that's a good thing. In fact, it means that it is telling you that the data is MCE or is missing completely at random, though as I mentioned to you, there are limitations to this work, obviously, because we already saw that the data is MAR. But still, that is a good thing, which means that we can apply our imputation later on. We can apply our imputation, but still bear in mind this aspect of missing at random. Okay, we are going to talk about the imputation at a later point. But I just wanted to show you here, you can run the MCAR test and see if your data is missing at random or not. Then there are the results like missing patterns. I'm not getting into all these details here. Okay, it tells you how many values are missing together. For example, here you have a missing pattern, two of the variables is missing. You might have more like that. You might have another one which is missing on its own. Here, for example, there are different missing patterns that can be found in the data, but we are not going to discuss all these in details here. It's not the purpose of this course. We are not getting into too much details, but still it is good that you know the little MCAR test that might help you to decide whether you want to impute. If you were to reject the null here, then you would be in some trouble. It would mean that you would not be able to do imputation. Maybe you would have had to remove some of the variables or get more information, things like that. Now that we have seen a little bit how to deal with these outliers, not really how to deal, but to diagnose these missing values and so on. What we want to do now, we want to, let me just find out this portion of codes where I have been working with missingness diagnostics. So here we go. This is where we started with the missing next diagnostic, mutate ozone. No, yeah, did campus. So yes, we started the missing nest, though it was not missing nest here. So here we are starting with missing nest diagnostics. I'm not yet talking about the imputation or whatever so far, but we will discuss that later. Vitals MCR test. So that's what I did here. In the first step, I basically look at the profile, and now I'm going to talk about the third step about cleaning some text. Okay, so we are going to do text cleaning. When I'm talking about text cleaning, what do I want to do is that I want to trim or standardize different categories. To start with, we are going to do some amendments to our text. Let's just go quickly here and talk about what we want to discuss. I'll remove all the filter here, and then you will see, for example, this I've already dealt with, but you have this issue of BSc written very inconsistently. You see, for example, MSc written capital M, capital S, capital C, but here it is written as capital M, capital S, and C. So we want to bring consistency in all these different levels of the degree level. And then we want also to check the payment methods. The payment mode here, again, you will see that there are moments that it is written C capital ARD, and then there are moments that it is written as C capital C small letter ASH, things like that. So we want to bring in again some consistency on all these, just in case to so that when later we change these to factor, we get consistent levels and we don't have all these kinds of things appearing. So let us try to work on that for a moment. So we'll start by doing the text cleaning. So what I want to do is to modify my current data frame that I have already. Let me just check quickly the data frame that we have. Here we go. This is our data frame as it is with the event uh, amended and so on. Now we want to change that current data frame. So we put df and we'll say df, we'll put that piping operator here where we will apply mutate again, where we will apply mutate. So what are we doing here? We are basically taking the data frame and modifying the different columns in that data frame. So I'm going to apply mutate here, and under mutate, let's do that. So under mutate, what I'm going to do is under mutate, I will change the degree level that I have. Let us recall the different names that we have: glimpse of df or strdf glimpse. So we have here degree level, as you are seeing, and then this degree level we want to change them. How are we going to change them? If you have capital MS, capital MSc, for example, you want to bring all these to a consistent writing like MSc, like this. That is correct. So we want to do something. How are we going to do that? We can do degree level, we say, is equal to case 1. What is this case 1? What we are writing right now is under the mutate function. This case 1, let me just do an enter here, and then I put this here, is what? This case 1 is a bit like an if-else statement, if you want. It's like a bit like an if-else statement. So you will say that you will check the case when number one, degree level is equal to, let's suppose, BSc. We to be able to do that, I will bring everything to small letter. I will bring the degree level to small letter. STR to lower. This is a function that I need to use, by the way. I will say that when str to lower, degree level is equal to BSc, but I can't say equal like that. I need to do double equal, because if I put an equal like this, it means that I'm assigning this function to BSc, which is not what I'm doing. I'm just saying compare any degree level that you have with that small letter BSc everywhere, lowercase everywhere. What does this mean? It means that it will go in degree level and identify what this is. It is B, S, E, capital, B capital, S capital, C capital. So what does it do? This function will change that B capital, S capital, C capital to small letter B, small letter S, and small letter C. You may say, but why would I want to do that? This is just a consistent approach so that we get the final result in the end. I will show you what is going to happen. But the issue is that if this B and S were capital and the C was capital, just like in the case of MSC here, it was capital as well. That principle will bring everything back to small letter BSC like that. But then I will say, if you have something like that, then what you have to do is to return B capital, S capital, C capital. So what you are doing here is that if BSC is written in any way that you want, it brings it consistently to small letter, but then it changes it back to BSC. In other words, I'm not changing this basically for the first one. It's just as it is. But it's an approach because I can't visually identify one by one. That's why I bring everything to small lowercase and then I change it back to this B capital, S capital, and C capital. So then I will do the same thing obviously for MSC. So I'll just copy that code again here and paste it down there. I'll just change that MSc. I will look for everything degree level. For example, when I'm doing str to lower degree level, it means that it is going through the all rows and converting everything to small letter. So this capital MSc is converted to small letter MSc like that. But then when it has identified the small letter MSc, it will replace it by capital MSc as you are seeing. But then there is another option is that you need to leave everything else as it is because there may be PhDs as well there. So as far as I recall, in the data, we do have PhDs as well. So we will leave everything as it is normally. So if you look at that filtered, you will see that there is BSc, MSc, and there is PhD. So we'll need to keep the PhD as it is. We don't want to change anything else. We leave them as it is. How do you leave everything as it is? So you say true is degree level. When you write this true is degree level, so this case when scenario, what is it going to do basically? This case when scenario will go through the whole code. This case one scenario will go through that first step, identify a small letter BSE, then replace it by this. Then it goes and it identify, for example, MSc. So for the first one, it's BSE, it identifies it and replace it. Then it does the same thing. It goes for the second step and identify. Okay, we go to the next one, next case. And when we go to the next case, that is the next row, we see that BSc is not there. So we move to the next case here, which is MSc. And MSc is correct because this MSc has been transformed based on that function here to small letter MSc. So then when it has seen that it is small letter MSc, even though it appears as capital MSc because we have applied that function, it converts that to small letter MSc, then it replaces it by MSc capital. So that's basically what's going on. And when we say true is equal to degree level, it basically means we keep everything as they are supposed to be. We don't change anything. So that's the first step of the process. And then the next step is that in the mutate itself, we want to do something else. So this is for the degree level, but in the mutate, we have another column that comes in. What is this other column that comes in? So first of all, we have done the degree level. Then you put a comma here to put the next variable. What is the next variable? Is that we want to check the payment mode, and we want to do an amendment on the payment mode. So the payment mode is, again, we are using the same principle of case when, as you are seeing here. And then I will put this just to ensure that I don't forget the bracket here. Okay. So, what are the different things that I want to do here? In the payment mode, we want to do something with respect to the cash here. Let me just give you an idea of what we want to do. I've already mentioned that, but I'll just go briefly over that. So you see that there is C capital ARD, and then you see that there are different ways things are written. At times it is written C small letter a, C letter small letter, etc. And then you see that there are unknown, and then you see that there are online. All these card is written as a bit like that. So you can do a bit the similar thing that you just did here. So let me just do that. Mm. I could repeat exactly the same thing as I did up there, but I will just do something a little bit different just to show you a different way of proceeding if ever there are some other instances. Let's suppose I come here and instead of having something like cash here, I get payment by cash. Now, everything else stays as it is. I don't want to have something like that. I would prefer that it is written as cash simply or cash like that, whatever you want, rather than payment by cash. But if you got something like this, then you need to be able to know how to deal with these. So how can I deal with these kinds of things, especially when you have messy text? So we first of all, we will go as we did earlier. We will do the str to lower as usual, just to bring everything to lowercase. That makes things a little bit easy to deal with. And we are going to change it to payment mode, as you are saying here. We change that to payment mode. And then what I do is that when it converts everything to lowercase, if for example it was payment by cash, I suppose it will be changed to small letter p meant by cash. Okay, everything will be converted to small letter as usual. But then the next step would be to detect if there is any cash in the particular word that we are in the particular case that we are dealing with. If there is a if it detects cache. How can I detect cache? It means that I need to write another function that is here under the str detect, which is under the str to lower. We say str detect. All right, we say str detect these. So what does this str detect means? It detects if in that particular string that you have converted to lowercase, payment by cash, for example, if there is this word cash here, because I'm putting it as lowercase because everything is supposed to be in lowercase here. When I've done str lower payment mode, everything has been converted to lowercase. So if it was payment by cash, it would be small letter p, and then everything will be small letters, so lowercase. So here we go, we do str detect all that. So that's basically another way of dealing with the same kind of issue, but it deals with more messy text if ever there is anything like that. In our case, there is none of this. That same principle would have been okay if we did it, but I just wanted to show you something different, especially when you're dealing with other types of text. And then you will say that we do the same thing like I did earlier, tilde, we replace it by capital CAH, cache. So we replace it by capital CAH, cache, as we just did here. Okay. Now, this is title case method. Then we do the same thing as we just did here. We replace it by, we have cache, we have card. Let's not forget that. Then this is going to replace by card. And then we do the same thing. and we replace now there is online as far as we remember here there is online. So there is payment method, there is online. So remember that everything is in lowercase. That's why I'm writing everything is lowercase on this side. So it detects if there is online in any particular word. If in case the word is written uh, with some other words accompanying online, so then it replaces it by online. And as usual, we will do true for anything else. And in our context, if you remember clearly, there is the example of unknown. We don't, you will see that here. When I say, you remember in the previous example when I said degree level. When I say degree level, for example, if there was PhD, PhD would be returned. If there was even missing values would be returned NA. But in our example here, you can, if you want, instead of saying return uh, payment mode, you could do that. There's no problem about that. It will return. There's no, because I know the data, but still, given that you know that there are things like unknown, you replace everything by unknown. So that becomes another level of your data. So you will have the first level cache written. Everything is written consistently as you are seeing here. So let's just check if everything is closed properly. We have the brackets covered correctly. So then we can just run everything here just to see if these texts have been converted correctly. So we run everything. We just do view df again and just have a quick look at degree here level. You will see that everything has been consistently written. You can just check if there is an a because of the true, you remember, is equal to degree level. That's why the true is degree level. That's why it is an a here. Everything is fine, so we have PhD is left with PhD. So then let's move to the next one, which is how do we say, which is where is it? Uh, on payment method. Where's the payment method? Let me just find this for a moment. I think it should be somewhere here. Here we go. The payment method here, the payment mode, you have cash, online. You see everything is written consistently the same way. Unknown is unknown. Everything is written properly well. So because there was no missing here, so if in case there was missing, you can replace it by unknown anyway when you are doing that. So we have done some cleaning. Now that we have gone through the uh, missingness and text cleaning, we are going to do a fourth thing, which is going to be removing duplicates. All right, we want to remove duplicates. How are we going to remove duplicates? First of all, you will recall earlier that we have been mentioning that there are some duplicates. You would recall, for example, there is row 9, 1092 here, which is exactly the same as that row down there, 1092, and the same thing applies for 1095. All right. These are two rows that appears twice, and we need to delete one of these copies of these from the data, these two. And then, apart from that, we've also observed that there are some issues pertaining to the, um, how do we say, to the record ID, where you have, for example, record ID like 1029 here, which is repeated. Of course, these are two different rows, meaning that they are two different data, but they do somehow have the same record ID. Now, there are different ways of dealing with that. We may wish to uh, go and identify what this could be. Maybe it's a different record ID. There could be many reasons why this is like that, but we are not going to get into all these details right now. We will just basically delete one of them. All right, we'll delete one of them, and generally we will delete the one that is after, that is 1 day later. For example, we'll keep this one and we'll delete this one. That's the approach that we are going to adopt here, which is not necessarily the best, obviously, in terms of approach, but we'll use that approach just to be consistent, where we delete the second the second record in terms of date. So we'll order them by order ID, and we'll order them by, not order ID, we'll order them by record ID, and we'll order them by date as well, and we'll delete the second one each time. As I said to you, it's not necessarily the best approach, but we are going to adopt that just for this exercise here, okay? So let's get into that quickly, and we are going to go in. Here we go. We are going to remove these duplicates. To start with, we are going to do the amendment in the data frame itself, and we'll say data frame. We will do pipe, and then from that data frame, what we want to do is to obtain distinct rows. All right, so when I'm doing that, when I'm saying obtain distinct rows, this automatically, as soon as I stop here, for example, if I just stop here, what's going to happen that it will remove these 10 these two records that are exactly similar. 1092, which is the full row, the full data is exactly similar as the 1092 above. 1092 here, you will see here 1092, these two records are exactly similar. So when I'm just writing that here, this automatically delete that. But as I just mentioned to you, I don't want to stop here. That's why I'm going to apply another piping here, where now I'm going to arrange. You would recall I just mentioned to you, I want to arrange the data in terms of order, record ID and date. So that's basically what I want to do. I will arrange the data in terms of these two criteria. What are the criteria? We have record ID and we have date, which, by the way, you would recall earlier, we have already converted by date. It's very important that we did that conversion in the first instance here, or we could have done it now if we did not do it earlier. So you would recall that this is very important, because otherwise it will probably order in lexicon form, and lexicon form is not the best thing. Lexicon means in alphabetical order if you want, but it's not appropriate. So we need to ensure that it is correctly written in the format of date. It is not a character, and then you can apply this ordering here. Otherwise, this would not have made any sense. Then we apply the pipe operator again, and when we have arranged the data in order, we want to delete that rows, that the second row. For example, let's suppose I was referring to which one? Where is it? 1029, for example. So in order of date, if it is ordered in 1029 is here, you have 1028, 1029, this is already in order. But then you have the order, these 1029, they are ordered according to how they are actually right now. By the way, the 7 2024 will be kept, and I want to delete the second. This applies for all the rest that you have. So then what happened is you want to do, but before that, let me just do a df quickly, and then we sorry, let me view df, and I keep that so that we can do the comparison. Okay, so let me just put that here, so that we can do the comparison later. And then you can do delete these record by record ID. So we will delete the record by record ID, as you are seeing me writing right now. We will do record ID underscore ID, and then we will, to be able to ensure that we keep the second row, we'll need to delete the first row that would appear. So distinct, if there is a duplicate record ID, keep the first row. That's what I want to do. Dropping any additional rows with the same ID. You keep the first and drop any additional row with the same ID. If there were 234, it will delete the 234 ID that comes afterward. The rows, I'm repeating, the rows come related to that. So what do we do then? We will need to do keep dot keep all. Dot keep all is just um, it's just the argument. We don't use keep all. The dot keep all is the argument that is used in distinct to be able to drop the next IDs. That is, you keep the first and you drop the next ID. So I'll just run that quickly, and then we will check again. When I've run that down there, we will check again view df. All right, the next one. So we view df again just to see briefly what are the changes. So I'll just bring that to the right, and then I'll fetch the next one. So here we go. Quickly, we just have a quick look at these, and then we will recall, for example, the last two observation that was here. All right, the last two observation that was here. Let me just try to find it out. um, 10, you see there, 1092 down there, and where is it? Just give me a second. I need to automatically increase that. So you have 1092 and 1095, which were there. So in the new one, let's have a look. 1092 and 10 1092 and 1035 is over, it disappeared. The next one, you would recall earlier, we add 10, let's just take only one example so that we don't take too long on that. You remember that there was 1029. Let's just check that. You can check the rest afterward yourself. You see row 29 and row 30, there was 1029 eben réduit. Normally réduit should be removed. So let's have a look. 1029 and see if réduit has been removed. 1029. Here we go. And you will see that eben is kept, réduit has been removed, as we are seeing. So we have been able to apply the removal of the duplicates, as you have seen. Now we are going to look at imputation. All right, let's talk about imputation. Our next step is to impute. Now, when we are going to impute, we're not going to do complicated imputation in this class. We are going to take very basic imputation, where we are going to impute by, for example, a constant median or mean or whatever you want, but we will take the median in this particular example. And when we are doing an imputation, as I mentioned earlier, there is this idea that the data is missing at random. And if the data is missing at random, means that it is conditional on a different variable. And if you're talking about, for example, you want to impute electricity, you might want to take into account the months as a factor, and also a campus as a factor to be able to impute electricity, because you will assume that the electricity will vary according to campus and, of course, according to months. All right, because of consumption during winter is not the same as summer, things like that. Okay. Now, the on the other hand, if you want to impute ozone, maybe you might want to use month as as a factor. And then if you want to impute solar radiation, then obviously there you don't necessarily need to use any factor. You can use a single mean that is replaced everywhere. So let's start by doing that. We are going to take into account, we are going to update the current data frame with using the piping operator as usual. And then we are going to carry out the different imputation. All right, so um, we will say mutate, open the bracket. Maybe I can just, yes, open bracket, and then, oh, I can do that like this to make it a little bit easier to work with later. So I put this here. Now, mutate, and then under mutate, I will write, I will create a column for months. Don't forget that mutate is about creating column. So I will create a column for months, and I will extract the months from the date variable. I will extract the months from the date variable. So for example, I extract the first month. If you carry on, you will see the second month. So I just want to extract the months only. So to do that, I will do as integer, and then I will say format months as integer, format, and then I will say date, but I will extract only the months. I do it like this. Okay. So that will create a new column at the end where you will have only one, two, three, etc. That's what it will do. Why am I doing that? I'm just extracting these months, of course, for the grouping that will come afterward. And what grouping? So let me just do that. After you have done this mutate. Now remember that we are assuming that this date is indeed a date format and not character or whatever. Okay. Now we go on to group by. We are going to group by campus and month together for the case of imputing electricity. So what do we do then? When we group, we will need to ungroup afterward, but we group by campus and month, and then we are going to impute this electricity. So we are going to create a new column. Again, each time you see mutate, you know that we are dealing with new columns. Okay. So we are going to do mutate, and then I will create a new column that is not in the data called electricity IMP, which means impute, and this is going to create a flag. All right. What does it mean by flag? It will return basically whether there is an integer, whether there is one, there is a missing value or no missing value at a particular electricity. Uh, Let me just go back to, or maybe I will go there, it will be easier. So for electricity, you will see here, for example, at the row 15 here, there is a missing value. So what it will do, it will create a new column here, but we will maybe at the end, not here. It will create it at the end called electricity impute, and everywhere will be 000, and this would be represented as 1. So that's what it is doing. You will understand why I'm doing that in a moment. So what we do here is that we create as integer, we say is.na, and then we put the name of electricity um, here. Where is electricity? So let me just do glimpse of the F to make things easy to locate the electricity. So here we go. We write it exactly as it is Na electricity. So when I'm doing that, I am basically creating a new indicator variable that we will refer to as a flag. It will flag 1 if electricity, and it will flag, of course, 0 if there is no electricity. Um, then, when we are done with that, our next step would be obviously to impute the electricity. We want to impute that electricity. How do we impute that electricity? We will say electricity kWh. That's that is basically that means basically that I'm overriding the current one. You will say equal to if else. It's a bit the same thing as the how do we say? It's a bit the same thing as the case that we were doing, but here you are using if else. In if else, what are we going to say? We will say is dot na electricity kilowatt if, what does this mean? If in electricity kilowatt we observe there is a missing value in a certain row, you are going to replace that by the median of that electricity kilowatt. You're going to replace it by the median of that electricity kilowatt. So you put comma and then you write median. This is a function that is used to represent median. So I'll just put an enter here, and to make things easier, we put it like this. So if a missing is identified, this is what it does. Is.na means it identifies there is a missing. What you do, you are going to replace it by the median. But the only thing is that when you are computing the median, you need to exclude any missing values so that it works properly. Otherwise, it may not be able to compute the median. It's always good to do that. Remember that when I'm doing that and a dot rm is equal to true, I'm not removing all the missing values that exist here in the data or anything. In fact, the idea is that I want to compute the median without considering the missing values. So in other words, it means that I'm disregarding all these missing values to compute the median. But the median by what? The median is being computed by campus and by month. So we are taking all eben. Let's suppose I want to impute that. This relates to what? It relates to eben for the first month. So what does it mean? It means that I will need to identify all electricity that we have for eben and month one. That is, I can filter by first month and filter by eben, and then I will get a series of electricity values. I just need to find the median from that, and it will be replacing this value here. That's basically what I'm doing. But to be able to do that, of course, I will need to disregard all these missing that exist to be able to do the computation. And then, comma, we are going to keep everything else as it is. Everything else as it is means what? It means that if there is any other value of electricity, you leave it as it is. Don't replace everything, obviously. Don't replace everything. So you put comma here and then you do replace by electricity kilowatt. All right. You replace by electricity kilowatt. So that's the kind of manipulation you want to do. So this is just to replace electricity. There is also something else that is important, is that we have this mutate here. Just give me a second. I'm just checking if I did not forget any bracket here. So this bracket goes with that. This is good. This is there. So very good. And I've got a bracket missing here that I've removed. So I just put it back as it is. So you've got a mutate that is changing electricity and replacing the electricity with a median as you are seeing here. Next step is that we want also to mutate something else. We want to mutate, we want to impute rather what? We want to impute now, for example, ozone. We want to impute solar radiation as well. So let's start by ozone. To be able to do the imputation, when you are doing that, when we are going to run everything at one go, it's good that if you have done a grouping by campus and month, you remove that grouping now. Because if you don't remove that grouping, because listen to me, you are going to select everything and run. So when you are running everything, it knows and it keeps that group of campus and month. But now you can't keep the campus and month because for me, I want to group only by months now for the case of ozone. So if I want to impute only by month, I need to do an ungroup again. That is, I bring the data back to its original state by removing the grouping, and then now I can repeat the step of mutate as you are seeing here. I can continue with that step of mutate. And mutate is about what? Your mutate, you will create the same thing, ozone impute and ozone ppb. So you have ozone ppb, and then you have ozone impute. You create a flag indicator just like I did earlier, and then you will do as dot integer, and then you will say is dot na ozone, let's write it down properly, ppb. So we are doing the same thing. You create an indicator variable. When you have created the indicator variable, you will use that particular indicator variable to be able to do your um, imputation if you want. In fact, sorry, I'm wrong there. You are not necessarily going to use that indicator variable in your imputation. You are using it just to flag which rows are. Um, Excuse me for that. I've created that. We are not using it here because there was no need, all right, to use it. You could say if else electricity impute is equal to 1, and then you replace the median. but there is no need for that. You're just using it to keep a record of where you add a missing value rather. I was saying something wrong here. Just please, sorry about that. Normally, when you're creating this integer, it's just to keep which rows are supposed to be missing. You're keeping a flag, as I mentioned earlier. So excuse me for what I just mentioned. Now, we get back to ozone PPB. We say if else, we say if else again, if else what? If else is an A PPB, what do we return? We return the median of, we'll just copy that as it is. Return the median of ozone PPB. Otherwise, we keep ozone PPB as it is. All right. So that's basically what we want to do. When we have done that, we again need to repeat that same procedure of ungroup as you are seeing here. And then we are going to do a last mutate because now we have to work on the solar radiation. So we do a last mutate. Solar impute. Maybe to make things a bit easier, I'll just copy that and paste it here as integer just to keep a flag of the solar radiation to know which row there was. Because when I'm going to impute, you won't now have a record of which one was missing or not. So that's why we are doing that. So we are going to create a new column called solar impute, and then we are going to modify the current impute. We are going to repeat that same procedure here. But the only thing that is important to note here I've done ungroup, but I forgot the important thing here is that in this particular example, before I do the mutate, I had to group. I had group, but I had to group back by month. So I will need to do group by here, excuse me, group by month again. And then you do the mutate, right? So you have ungrouped, that is, you no more have this grouping that was there, campus and month. Now it has been ungrouped, but then you group it back to month, and when you group it back to month, you need to ungroup again. And here you will see that I'm not doing any grouping. I'm not doing any grouping means that you will have a constant value being filled throughout this column of ozone. But here you will not have a constant value filled for ozone, sorry, for solar radiation. Here you will not have a constant value filled for ozone. You will have maybe 12 different values if you have 12 different months, because you have grouped by months. You will have 12 fixed values that will be imputed. For example, here you will have, let's suppose you have three campus by 12, you have 36 possible values somehow if there were 36 missing values, let's suppose. If you have more than 36, you would have many possibilities, because what I mean here, what I want to say is that if you're grouping by campus and months, what does it mean? It means that you have median that can be computed for the eben month 1, eben month 2, eben month 3, and so on. So you have 36 possible values that you can use to impute. If there were maybe, I don't know how many missing values you had, but you could use any of these 36 depending on what is missing. If you have a missing for month 1 in a band, you can find it. you see. But here you have only 12 possible values that can be used to impute. But here there is only one possible value that can be used to impute. It's the median of the whole data set for ozone, the whole column for ozone. Not ozone, excuse me, I'm saying something wrong. It's solar radiation rather, for solar radiation. So what I will do here, I will say solar radiation is going to be imputed using this, replace that, and I keep that as it is. So we are going to run that and to do the imputation. But before we do the imputation, I just want you to view the DF as it is right now. We keep it that as it is. Here you will see that there is solar radiation. Let me just move on the right. You will have solar radiation here. We can just check the first one and the 12, etc. Let's just move a little bit on this side, and then we minimize that. This is what we have for the time being, and we just run this step of imputation. Sorry, by the way, let me put the hashtag here. So let me run this imputation and we'll see what happens. So we should have some issue somewhere. We forgot a comma here. That's one of the issues. Let me just check if there is anything else. Electricity. That should work. So let's just run this and see if there is any other mistake. We'll try to find out. Okay. So you will see here. Just look at this. The error down there. You will observe something is that each time there is an error. Look at that. There is plus plus, which means that it is taking the old code and continuing. But coming here, there is another issue that goes on. So we can see that sometimes there is a bug going on. Not a bug, but the way I've written it should not be written like that. I would prefer just to write it a little bit differently by starting the function with each other. Let's start from here just to avoid any mistake. We'll delete that space so that it doesn't take it wrongly. Then we are going to do the mutate again here. We're going to do mutate again here, right? And this mutate as well here. That should partially solve the problem. Maybe there might be other problems as well. We are going to check in a moment, but it's at the same time we are doing that. It's good that you can identify if there are any issues. You can also see if you get such type of issues, how to solve them. Okay, so that's not a problem in itself. So if else, we'll start a function by the name itself. So if else, I'll start it here, maybe just to avoid any issue. But anyway, it doesn't matter for this one. Even if I start it here or not, it doesn't matter because it's already bracket is already there. So maybe this time it should work, but I will give it a try and check again. If there is any other mistake, we will get to know which one, what these mistakes are about. Okay, so let's just run this again and see if it works. If not, we'll see where the problem is. So it works, as I just said here. We just needed to check where the problem is. So unfortunately, I've removed the first view, but it's okay. We can view the DF now again, and you will see that they have been imputed values for the different columns. For example, here you see solar radiation. There is no solar radiation at all, which is missing. There is no missing for ozone. They have been imputed correctly. You can just verify yourself now to see if the imputation has been done correctly. You will see which one have been imputed. You remember these? So you will see, for example, in solar imputation, there is one here, there is one here. So observation 2 and observation 13. Observation 2 and observation 13 for solar radiation should be the same because we have imputed a general one. 2 and 13, 212.8, 212.8, so you got a single one. Whereas for the case of ozone, it's different. For electricity, it's different. You will not have a single imputation everywhere. So you can verify that on your own. Deal with outliers. Let me close this. So we'll get into the next step, which is to deal with outliers. So we are going to deal with outliers now. Now, what are we going to do in this part? What we want to do is to normally identify our outliers, number one, but also windsorize. You remember? We are going to windsorize. Windsorize means you're going to cap your revenue and win both. We are going to work for revenue and win data. We are going to cap the revenue and win on a certain value, obviously. You will see that later there is a negative value for revenue. For example, you don't want that negative value as well. So we want to do something about this. So we are going to do to identify our outliers using the IQR, that is the interquartile range method, as I mentioned to you earlier. I'm not going to use standardization to find it, but we are going to use interquartile range in this case. So to start with, what we might want to do is to start by a quick box plot. All right, we want to start with a quick box plot just to have an idea about what are the outliers that we have in this data, and then we will proceed to windsorize these and so on. So let's start by the first step, which is to identify to draw the box plot. So quickly, there is a function that we call box plot that you can run, and we are using base R here. If we are using base R, we need to use the F dollar each time because we are working. We have not attached the data at any point in time. So we want to work with. Let me just do that again so that we can see the variables and we can copy and paste them. So we are working with revenue. Where is it? So this is the variable that we are working with. So box plot of data canteen revenue. You can put a title to it. You say main revenue, etc. But I'm not going to take too long on that. So I repeat, if you want to put a title, you do main equal to between inverted comma and write down something there. But just for the sake of time, I'm not going to take too long on that. So I will do a box plot as well of the where is it? We want to do a box plot of win as well. Here we go. I'm choosing these two variables here just to identify if there are outliers, and you can do the same check again afterward for other variables if you wish. But let me just run these two. And here we go. We've got number one. Let me run the canteen. You see that there are outliers clearly here for the canteen revenue. And you see that there is a value of zero, but this value seems to be a bit lower than the zero here, that whisker. So, which indicates, well, if you see it, if you don't see it, it doesn't matter. You can go in the data, you will identify that there is a value of negative 500. So in any case, we have to deal with that afterward. And then we check all the win. Here we go. We've got the data. We've got some not negative, but we've got some values on the lower side of 2 and some values on the above 8 that we have to winsorize. And these are the outliers that we want to deal with. So to start with, we are going to get the exact whisker cutoff. All right, using the IQR rule. How do we do that? Let me just run the box plot again. Okay, and then we just add something. We do dot stats. When we say dot stats, what is going to happen? It will extract all the information with respect to this box plot, like it will give you the lower whisker, it will give you the upper whisker, and so on and so on. All the details of that box plot, the lower quartile, the median, and all these different things. Okay, so that's what we want, and we want it for revenue. here. And if you do that, we will need also, for your information, if you just run that, you'll see you get some information here, quite a number of things, but we are interested in only this one. So then I will need to do dollar. Each time I need to call something, I will need to do dollar again. And then that will give me only the stats here, that is a negative 500 and so on. Okay, that's what I will get. So what I will do, I will give it a name. I call it BR. Okay, and then when I get the BR, if you are interested in extracting that first number and the last number, what is the first number? That first number is the fence that you recall we have seen here, negative 500 here, and that whisker here represents the 24,300. So we will basically need these two values here. We'll need that, and we will need that. Now, this negative 500 is not being treated as an outlier here, but we still need to deal with it because we cannot have a negative value, obviously. So what are we going to do now? We are going to continue. We have obtained we can obtain only these values, and then we are mostly interested in only the lower one and the upper. Now sometimes we refer to that as a lower fence, and we refer to this as the upper fence. Okay, now we have a lower whisker or the upper whisker in this particular context. So we can extract them, by the way, if you want BR1. If you are BR, if you, I did not call it yet. So if you run these two together, if you call BR1, you will get negative 500. And if you want BR5, that is the fifth value, 1, 2, 3, 4, 5, you get the maximum. So you can run it, you will get the highest non-outlier value if you want. This is the lowest non-outlier value, which is also referred to as the lower whisker cutoff, and this is the upper whisker cutoff. So we can do the same procedure now for win. So we'll just replace this by W, and we can obtain for win glimpse. We change that. And here we go. We are obtaining the object that relates. This is called an object here. BR, that is going to give us all the stats as we are observing here for canteen revenue. And BW will give us all the stats for, of course, win. Okay. Now, having done so, we will want to use these information, especially the BR1, BR5, BW1, and BW5. So if you do BW1, you will see that gives you 2.16. That is a minimum value. And then BW5 will give you the maximum here. Now, what do we want to do? We want to winsorize these outliers, for example. We want to identify where the outliers are and also winsorize them. So what do we want to start with? We want to flag revenue when there is an outlier by 1. If it is below BR1, we'll call it 1, or if it is above BR5, we are going to call it 1. Else it becomes 0. So we are going to just a bit the same principle that we did earlier for mutate here. We are doing the similar kind of thing here, all right? So we are going to replace our data frame with pipe here as usual. Now we do mutate, open bracket, and then close bracket. Now in mutate, you want the outlier flag, if we want to call it like that. So you will do, let's call it like this, rev outlier. All right. Now, and then this is equal to, we want to do similar like what we did here. We do it as dot integer. So we are revealing our outliers by using as dot integer, and then we are going to check if the value is less than b1. That is, if the value, you recall here, let me just run this graph again. Yeah, so the graph is somewhere there, let me show you. So if the value is less than b1, this is b1, this is b5. So if br5, this is br1. So if the value is less than br1, it's going to be treated as outlier. If the value is greater than br, it's going to be treated as outlier. Now that you have understood that, so we are going to check that again. So we have to say if, not if, but as in teacher, whenever the canteen revenue is less than BR1, you would return um, 1 over was, or can write or using this vertical bar. You can just find it on your laptop. If this is greater than BR5, we are going to return 1. This is what is going to happen, right? So what we are doing here, we are saying we are revealing our outlier such that any value that is below BR1 in revenue, or any value that is above BR5 would be treated as an outlier. So that's the first step. We want to do that. Then we want to Winsorize these different values. So when we're talking about Winsorizing, we will give it a different name. Let's call it revenue underscore W, which represent obviously Winsorize. And then we use pmin. Now, I'll explain to you what the pmin is in a moment. When you are using pmin or pmax as well, let's write the pmax and then I'll explain to you. Pmax, pmin, and then pmax of canteen revenue. You'll see there I don't need to write because it is from df itself, so there's no need for me to put df again. So I will write pmax br1 and then pmin br5. What does this mean? What did I write here? I'm basically saying that this pmin is a function that cap any value above the upper whisker BR5. So the pmin is for the BR5. So if the pmin is for BR5, it caps any value, what value? This value that you have here. It cap it um, cap any value that is above the upper whisker down to that BR5. So if you had 100 here and BR5 was, let's suppose, 20, this 100 that you add here would be converted to 20. That's what it means. On the other hand, you have a Pmax here, which is going to lift any value below the lower whisker BR1 up to that value. Any value that is below this BR1 up to that value. In our context, we don't have any value that is below BR1, so it doesn't matter much. Everything will be already as they are. But the Pmax, what it is doing, I repeat, is that it lifts any value which is below that lower whisker BR1 up to that value of BR1. So if, let's suppose BR1 was negative 500 and you add negative 700, that negative 700 would become negative 500. That's basically the idea of this Pmin and Pmax that we are doing. But the thing here, we have another issue. Let me just correct for that issue. We want also revenue W we want the revenue W to ensure that there is no negative values for the revenue. You can't have a negative value for the revenue. So what do you do? Then you will use, if you just understood what I just mentioned to you, if you just understood this principle, you can pause the video and try to think whether I need to use Pmax or Pmin. So what is the idea? Is that any value that is below zero should be converted to zero. That's what I want to do. So shall we write Pmax or shall we write Pmin? Just pause the video and think about it, and then now you can check. So the answer is Pmax. We will need to use Pmax of the revenue of W that we just compute up there, of that revenue W that we just computed here, and we'll replace that by obviously, so we'll cap it to zero. So any value that goes below zero within revenue will be capped to zero, as you are seeing. That's the idea. Then we're just gonna have to do the same thing for win outlier. We put another one. We are going to create, but for win outlier, we don't have the issue of negative, so it's gonna be all fine. So we say win outlier, and then I repeat the same procedure here. Maybe some change in the values. So as dot integer, and then we are going to replace the win MPS here as an integer. We replace that win MPS less than not BR but BW rather this time, and this is changed and this is BW. You would recall what BW is here. Okay, BW is from these stats. So let me just check this so that I don't do any mistake. As that integer, df win MPS is less than BW1, df is greater than that. That's good. So by the way, there is no need for me to write df. I don't know why I'm writing df here, by the way, because it's already in the mutate. Okay, there's no need there. I needed to write df. This is not necessary here. All right, we are already using mutate from, we are using the pipe operator, so there is no need. You see the pipe operator here, there is no need for me to write the df here, huh? It's just because I've copied and pasted it that's wrong to have a df here, dollar. So that's fine. Then the last step is, as I just did here, to find the win W, and then this is equal to, for the win W, we are going to apply the same principle that we just did here, P min, P max, as you are seeing here. Just gonna copy that and paste it here. So we just replace this can here by WPS, and BR will replace by W. This will replace by W. So that's the kind, in a nutshell, what we need to do for the outlier. Hopefully we don't have any mistake here. Let's try to see first before I run it. So let's try to run this df till the end. So no problem. So we can do view of df. Can do that. We can just check on the right here. They have created the new variable. We have got the two new variables created. So for example, here you have the reveal outlier for 17, which is revenue outlier, excuse me, not reveal outlier. I'm just saying something stupid here. Revenue outlier. And then you go for revenue outlier. Where's the revenue? So content sales. So you will see that there is the observation Let me just check again. It is observation 17 that is treated as an outlier. And you will see observation 17, you have 24,000, which is an outlier. That would be capped to the value of B5 that we have seen. And that value of the new revenue is not the same as it was earlier. Now it is 24,307.71. So the same thing applies for WinRW. You can check it on your own. Okay. Here we go. That was for treating outlier. You can also quickly verify the summary of DF, and let's just try to see what we get here. A summary of DF for, you would recall, for canteen sales. So sorry, we had revenue negative 500 here, but when revenue has changed, the new revenue is not, does not contain the negative value, but it contains a zero, which is a capped value, as we have done here. All right, so you can just check this out as well. Now we move on to the next step, which is transforms, transforms and scaling. Okay, so let's get into transform and scaling. That's what we want to do now. Okay, how are we going to go for transform and scaling? Uh, Number one, there are different uh, transform that you can apply, but we will do the log and we'll do the square root transform. We're going to apply these two mainly. And then we will do some scaling, of course, so using the z-score as well. And we also apply the robust method that I mentioned to you in my first video, okay, in the first part of video. So we start by df, and we say df as usual pipe operator, and then we do mutate as usual. We are going to do some transform, but transform will involve creating new columns. For example, I want to do the log of revenue for analysis later. So the log of revenue, remember that revenue here we have a problem is that it contains zero. So if you say revenue, log of revenue, that would not necessarily work. All right, that would not necessarily work. You will need to use another function that we call log of 1p. Log 1p, sorry. Log 1p means what? If there is zero, it will not compute log of zero because log of zero is not possible. So you will be doing 0 plus 1. That's basically what it will do. When you're applying this, it will do log of 0 plus 1. Okay? So we are going to write revenue, the one that we have dealt with for the outlier. Then we have there is another variable for the count. That variable you would Wi-Fi here, where's the Wi-Fi? We have Wi-Fi issues, which are basically count variables, even though the main is decimal, but these are count variables. And I was mentioning to you that the square root does a good job generally in that. So you can apply Wi-Fi. It was not necessary to do that as well. You can keep the Wi-Fi as it is if you want, but if you want, you can also do a transformation on that, and we can do square root of Wi-Fi of Wi-Fi issues. All right, there is a last one we want to apply for rainfall as well. There is rainfall in terms of millimeters. By the way, you could have dealt with the outlier issue again. I would encourage you to try it on your own for the other variables like temperature, rainfall. Identify if there are outliers. If there are outliers, you can deal with them as well. If there are no outliers, that's fine. We move on, but you can give it a try yourself. So, but for the rainfall, we want to apply log transformation again because we are dealing with a maximum of 150 and 10. So, if you want to deal with that again, we can call it rainfall log. Okay, and then this is equal to rainfall log is equal to the same thing here, log of 1p, and then we put the rainfall millimeter here, and then we close that, and then it's not over. Now these are where we are applying some transforms. We can just call it transforms, right? Using logs, we are fixing skewness and counts. If you want, we are fixing skewness and counts rather, issues. But now we are going to apply some scaling here, which is going to be, for example, the z-scores, right? Applying the z-score is relatively easy. You just need, let me do it for temperature. I will apply the z-score for the temperature. I will apply the z-score for the wind variable that we have worked on. And then I will apply for revenue. Okay. How do I apply the score for each of these? I can just use a simple function called scale. I just need to use this function scale each and every time. That will do the job. Instead of me writing x minus the mean divided by the standard deviation and so on, it's far easier to do it this way. So what do I do? Temperature Z will be based on temperature C. You are going to scale temperature C. Wind Z will be based on wind W. You remember the one that we wind surge using the based on the fact that there was outlier or whatever. So then we have a revenue as well, and we want to scale revenue, but we're not going to scale the revenue that we had earlier, W Windsor 1, but we are going to scale the revenue of log. You may wish to do that, by the way. Well, it's not compulsory, but I'm just showing you if you wanted to do that, you can do it. So don't forget your comma each and every time. And then when this is done, I want to apply the robust scale. What is the robust scale? It is a median by interquartile range. I don't know if you recall. This is what I'm referring to, right? You want to apply the robust. So in view of applying the robust scale, what do? We are going to apply the robust scale on the Wi-Fi data that we had, but on the square root data rather. And I will say Wi-Fi RB equal to, I will take the Wi-Fi square root that I've computed. I will subtract the median of Wi-Fi square root. Just in case if there are any missing values, by the way, this is a small trick that you can do, is that in any function like the mean, for example, you can do n a.rm equal to truth so that it computes the mean. If ever there is any missing value, it can still compute it. But I don't think this is an issue, but still we can prepare ourselves for that. Then you need to divide by the interquartile range, okay? And the interquartile range is going to be obtained by the function IQR. And of course, again, we do the same thing that we just did here. That's that's how we can deal with this. So let's run the whole thing. And so let me just run it again. It was not okay. Now we can do summary of DF just to have a better and quick view of what's going on. So here we go. You've got the Wi-Fi RB, which has been created, which is a robust scale measure. You have a negative scores and the positive scores as well for revenue. That indicates a lot that revenue can be highly skewed. Okay. Bon. Then you have Win, that we applied the scaling as well, Win Z here. So normally when you have values that are less than 3 and values that less than negative 3 and values that are greater than 3, that also indicates that there is the data is skewed a lot normally, right? So here we go. We have all these different information right in front of us. We can make sense. We can interpret them and just check what's going on. So that's how we can run transforms. Now our next step would be to do to apply a model. All right, we will apply a very minimal model just to apply an analysis. We are going to apply a very simple model application. And what am I going to do? I'm going to select some of the variables that I want to analyze here, and then I will drop all the missing values that I have from exam score, because the idea was to have exam score as a dependent variable, as a target variable. We refer to that generally in the context of data analytics, and that dependent variable will be based on some independent variables. So we want to check if exam score depends on, for example, temperature, depends on wind, revenue of things like that. We are going to select a few, but again, this is quite subjective here. We are just creating the model data frame, and we are going to say data frame, and from the data frame select only a few variables. What variables am I going to use? Let me just do glimpse again so that it makes it easier for me to spot them. So here we are. We are going to select some. First of all, obviously, we are going to select exam score. We should have exam score somewhere, which is our target. In fact, the target means dependent variable, obviously. Then we will select temperature to see what are the factors that influence um, exam score. But as I said to you, this is just subjective what I'm doing here. But I'm not using the temp Z, sorry, yeah? I'm going to use the temp Z rather. The one that we have modified, the one that we have standardized, and so on. All right. Then we are going to consider the win. Probably this doesn't have any impact on exam score, but still, I'm considering them. Then you have revenue of the canteen, probably. Then you have Wi-Fi, RB, which is now quantitative. And then you have also the campus, maybe that would matter. And that's all. So what we want to do, in addition to what we just did here, might want to you remember that in exam scores we had quite a number of missing values, if you will see here already. And I already mentioned to you in the course, it is preferable to avoid imputing missing values. Avoid imputing missing values and rather use a model as they are. If there are missing in the target, maybe the best thing to do would be to delete. Of course, as I said to you, it depends on the number of missing values that you have as well. But in that data, we don't have that many, so we can allow ourselves to drop these to drop the missing values. So what do? We come here and then we say pipe operator again, And then on the pipe operator, what I'm going to do, I will say drop NA, drop NA from exam score. So in other words, it disregard all the rows where you add an NA. That's what we are doing. We are selecting all the variables as you are seeing. We are creating a data frame which is going to be which includes only these variables as you are seeing here. Now, when this is done, we can run our basic, very simple model that we are going to say fit, which is our regression model. And there is a simple linear regression. For those who don't know what a simple linear regression is, I would kindly request you to go simple linear regression. I would kindly request you to go and study what a simple linear regression is, because this is one of the most basic kind of regression model that you might have. But here we are not running a simple linear regression, but we are running a multiple linear regression. You're running a multiple linear regression. Now, I would kindly suggest you to get an idea of what a multiple linear regression is and what a simple linear regression is. These are very important. In our context, I'm going to run a multiple linear regression. I'm not getting into the details of this right now because we will never finish here, but I'm kindly asking you to go and study this on your own if in case you don't know what it is. So then what I just need to do is to select the variables that I want to include, which are temp z, which plus win z. So maybe what I will do is that I will copy everything. I'll just replace um, my the comma by I will just replace the comma by a plus. Okay, sorry, excuse me. So we'll replace this by plus, we'll replace this by plus, we'll replace this by plus. I just want to ensure that I did not miss anything. Temp z, win z, ref z, so this is okay. And then we need to mention what is the data. The data is in fact the mod df, not the df. So it's always good to mention what the data is about. So we then can just run a simple summary fit just to have a look at it, and let's run all this as it is to get p-values and so on. So here we go. Based on that fictitious data that I've run, you will see that this is a multiple linear regression. You have the estimates, the intercept, which we don't pay too much attention to generally, but you will see that temperature is a positive value. So what does it mean? It means that as temperature is tends to increase, there is also an increase in exam score. Bon, again, you have to be careful here because this is a fictitious data. That doesn't necessarily mean that these values make sense. But you can also check these, how do we say, these asterisks. These asterisks generally imply whether your model is significant or not. For example, temperature seems to be significant and has a positive impact on exam score from this exercise. As I said again, this may not make sense in reality, but it's just fictitious data. So that's why I'm just drawing your attention toward that. Do not take these values as if they are correct or wrong. It's just a fictitious data, but I'm just helping you to interpret it right now very quickly without getting into too much details as well. But on the other side, revenue of canteen as it increases seems to have a negative impact on exam score. And again, it is significant because the moment that you have the asterisk, it means that it is significant to the 5% level of significance as you see here. So anything that is significant means that it is having an impact uh, on the target, which is in our context exam score, which is not rated by chance. Okay, so you have Wi-Fi RB, you have the Wi-Fi. All these are factors that seems to affect exam score. For the analysis, I would kindly request you to understand what a multiple linear regression is. Um, that's important. You need to at least have a basic idea of what analysis you can run. Like here, a multiple linear regression might be okay. Here we go. That's the a minimal model that I've run. And you can also run a simple linear or multiple linear regression for your assignment, by the way. That should be fine. I'm not expecting you to go for complicated models at this stage. Everything with a small report. Okay. So this is 8. So we are going to talk about now a small report of what we have done. Okay, you would recall here we are going to import, do the profile, clean. We are applying the model. We did not pay too much attention to that one, but you still need to understand what a simple linear, multiple linear regression is. But then we are saying that we are going to create a log accountability record of changes, scripted and reproducibility. Which is sorry, changes which are scripted and reproducible. So what are we going to do? We are going to create a small report just to provide information on what we have done, because if we have removed some missing values, what is the percentage of missing values that we had? It's always good to have an idea of your analysis, what you have been doing. So let's get into that. We are going to create a small report, and we are going to say report, and we are going to create a table. Now for the report we are going to create a table. Now you all understand what a table is. A table is just like a data frame, but as I mentioned to you, it's a bit of a modern version of a data frame, which is somehow nicer to deal with and nicer in terms of presentation as well. So we come here, we say we are going to create our variable. What are the variables? We need to state what are the variables that we have been modifying, changing, what are those which required imputation, what are those which were capped based on the outliers and so on. So we know that there are certain variables that we have been working with. For example, again, I like to do this glimpse just to get a quick view of my variables. So df. So we know that we have been working with electricity. So we just write it down in the inverted comma. Then we know that we have been working with ozone PB and solar radiation as well. So let me just copy both of these. So we got these, and then we've got solar radiation. We've got the wind MPS as well. That was modified. We've got the wind MPS that was modified. We've got also, let me just put this canteen revenue here. No problem whether you want to write it down. So we have canteen revenue as well. Then we are going to put a comma. Just then we are going to start mentioning the second column would be the percentage imputed. What is the percentage of our data that was imputed? To include this percentage of the data that was imputed, I need to go and identify how many were imputed. I don't know if you recall here. We There we go. We have kept a column. We kept ozone as well. We kept solar as well. All these we got are variables that will help us to determine whether we have imputed or not. Okay. And for revenue as well, we have been imputing, but we are going to check all this. Okay. So we start by the first, we are going to calculate the, um, let's start by electricity first, which has been imputed here. We're going to do an average, that's all, and at the end we are going to multiply all these by 100. So let's compute the Thibault. There I need to do the mean of electricity imputed, but I can't just call electricity imputed right now. I will need to call it from df because I'm not using the piping operator anymore now, eh? So then you are going to repeat that same step here for ozone. Close bracket. Repeat that same step for solar imputation. Then you repeat the same thing for mean. And you are going to look at the canteen revenue MUR. But this one for canteen revenue MUR, you can do is dot na, and we will put that in between is.na df dollar. So what are we going to do here? We are going to return any missing values that we have for canteen if there are. Maybe there are no at all, but we may return is NA canteen revenue means that it will return 1 and 0 if you have a, it will return 1 if you have uh, a missing, and then it will do an average as usual. And then yes, so we have solar impute, this is fine. I think I forgot to put the bracket here. Let me just check this quickly. Mean this is for that, this is for this, should work normally. So that's we also need to do something else. All right, we are saying C mean, and then we have win MPS. I forgot. Win MPS here. Normally, when you're talking about mean MPS, there is no imputed value for win. We did not necessarily impute any value for mean, so we'll leave it as 0 as it is. And then we'll take the whole thing, we multiply it by 100. 0 sorry, just going to close that and multiply by 100, and then I will do the additional part, which is the outlier capped. We have been dealing with the outliers, and we will do the capping now. In our context, what is a percentage of outliers that has been capped for electricity? We did not do it, so we put 0 here. We did not do it for ozone, we put 0 again here. We did not do it for solar or radiation, we put 0 again here. But for revenue outlier, for revenue, you would remember for canteen revenue, we would remember that we have this variable here from df. So we will say find the mean of that variable from the data frame. And then we also did the same process for outlier, win outlier. So we're gonna do mean df dollar and win outlier. So that should sum up everything, but don't forget to multiply by 100 because this is supposed to be in percent. Okay, and then we can just have a look at the report afterwards. Let's try this and see if it works. If it doesn't work, it's probably because of a comma or something. So it works. That's fine. So here we go. We got the percentage of, you got a small report stating what is the percentage of electricity that has been imputed, what is, but there was no outlier capped. So here you got 2.7% of the revenue of a rose in canteen revenue, which have been um, capped, etc., etc. So these are the information that you have. That's very good information to include as well if you are doing your assignment, such types of report stating what you have done. That's a good idea. So that sums up the video for today on data preprocessing as we have seen here. So just a quick, so we have just completed data cleaning and preprocessing. We have seen what, so we have done the reporting checklist, but here we have gone through this import profile clean model, and we created a small log which is a reporting checklist where you have percentage of missing. We did not do the plot here, but you basically got this done. These you can mention them if you have set seed and so on, but you did not do that as such here. Here we go. We end this class for now. Thank you for your attention.